This session is for mobile communications and network technology. We will have a very interesting, very important 9 presentations. So let me introduce the first presenter. He is Dr. Go Young-jo from ETRI. He is now Director of 6G Wireless Technology Research Sector at ETRI, and also he is a Chairman of the Technology Committee of 5G Forum. He will make a speech today on time, on rate for 6G radio. So let's welcome Dr. Go.
Thank you, Dr. Che. Good afternoon. I am Young-jo from ETRI. I am working with the Mobile Communication Research Division at ETRI. In this talk, I'd like to discuss some of the one-time on-rate technologies for 6G radio. So this is the outline of my presentation. I will start with our views on 6G radio capabilities. Then I'd like to proceed with the introduction of on-time on-rate radio technologies, followed by a detailed description of our research results on these selected topics. First of all, I'd like to describe our proposal for 6G usage scenarios. For 6G usage scenarios, we suggest to use a new term called usage element. Then we'd like to describe a usage scenario as individual usage elements or combination of usage elements. Based on our analysis of service and technology trend, we suggest to have 6 usage elements, namely ultra broadband, ultra massive connectivity, ultra high reliability, low latency, ultra 3D coverage, ultra low energy, and ultra precision positioning. Some of the representative usage scenarios for each usage element are shown in this figure. We think 6G should support not just individual usage scenarios, but also mixed usage scenarios. A mixed usage scenario is a usage scenario described by combination of more than one usage element. And the support of mixed usage scenarios, we think, will become a characteristic feature distinguished from 5G. From the perspective of communication technology, we think the support of real-time integration of digital world and physical world would be the most important characteristics of 6G. The extended reality, digital twin, cyber-physical systems in industrial IoT, autonomous driving, these are examples of applications dealing with combination of virtual world and real world, and requiring real-time interaction between physical and digital world. Communication service is evolving from the best efforts towards the high precision and guaranteed. A study group in IITP, which is a NET 2030 focus group, they predict ultra-precision service would become a killer application in beyond 5G. And ultra-precision service is based on ultra-broadband, ultra-low latency, and high reliability communication. And we expect support of various traffic demands in a highly precise manner in both the space and time domain would become the most significant part of 6G. To be more specific, low latency is in-time delivery of a packet. That is, a packet arrives before a pre-designated deadline, while high precision latency requires a packet delivery exactly at the designated instance. Practically, this means the arrival of packet within a finite time window. A prerequisite for on-time delivery is time-aware networking, such that entities involved in the communication share the common timing reference. On the other hand, we use the term on-rate to describe the capability of providing a required data rate anywhere. So on-time on-rate radio access is characterized by ultra-reliable, low-latency communication, providing a required data rate for anywhere, anytime. So in this presentation, I'd like to discuss these three outstanding technical topics for on-time, on-rate radio access. The first one is multi-point MIMO for uniform QoS. As we go further upward in frequency, including millimeter wave and terahertz, we are facing some serious issues. That is, non-uniformity of capacity in both space and time. This is mainly caused by signal strength variation across cells and increasing interference due to network densification. Moreover, the radio characteristics of high-frequency carriers produce significant shadowing and even blockage, sometimes leading to outage. In overcoming these issues, we know from almost a fact that multi-point transmission is a very good candidate solution, while at the moment, the current standards for multi-point transmission are not sufficient. Another issue is the high cost. High cost for multi-point deployment and operation is a headache for operators. Distributed multi-point transmission reception is basically a multi-point, multi-user MIMO scheme, utilizing coordination of geographically separated TX and RX points. So it can provide macro diversity through joint signal processing, and it can be used to create artificial multipaths, thus able to overcome the blockage issues. Through a proper coordination between TLPs, interference can be reduced, and beam switching handover issues can be suppressed. Ultimately, distributed multi-point MIMO has a potential achieving uniform QoS regardless of UE position. So, but, okay. Sorry. Okay, so technically we think these will be our key issues. Design of joint transmission reception methods based on multi-point cooperation, and reference signal design, channel estimation, and link adaptation, such as resource and power location. In this slide, we show our preliminary results for multi-point MIMO. We assume that a central unit is equipped with multi-TLPs, and the central unit performs beamforming and power control for all the TLPs. And here we assume ideal connection between the central unit and TLPs, thus incurring no latency in exchange of information between them. With this simple simulation setting, we estimate distribution of UE throughput for different number of TLPs with different TX-RX beamforming strategies. The number of UE is 20 here, with 20, 200, 2000 TLPs respectively, with zero forcing and MLT and MLT for TX and RX beamforming. The resulting CDFs of UE throughput are plotted here. And what we can see is a huge gain in spectral efficiency with increasing number of TLPs for both uplink and downlink. And those gains are obtainable regardless of beamforming strategies. So relatively more practical setting would be per TLP beamforming. That is, beamforming is done per PLP basis, thus not requiring channel information of other TLPs. On the other hand, the power control of TLP is semi-statically coordinated by the central unit through the exchange of simple information between the central unit and each TLP. The resulting CDFs of UE throughput are shown here, and these are what we have found. Significant performance gain with the power control compared with fixed equal power location. And again, the spectral efficiency increases with increasing number of TLPs. In this case, when the number of TLP is increased from 20 to 96. Next one is synchronization for mobile TSM. So again, in 6G, for the full realization of high precision services, we believe further improvements may be needed in areas such as URLLC, time awareness, and positioning. For time awareness, one of the most important application areas is isochronous real-time process in industrial automation, where multiple devices work together, performing highly time-sensitive operations. Those operations require low-latency communication and sharing of high-precision timing reference between the devices. For time-sensitive ultra-precision services, the end-to-end clock synchronization is essential. The most difficult part is time synchronization in wireless domain. Time synchronization needs to cover devices wirelessly connected with the same base station and devices connected with different base stations, and even between devices in different network areas. So these are technical considerations for absolute time synchronization. First of all, designing synchronization signals and mechanisms that are robust against the RF impairment, such as phase noise, frequency offset, IQ mismatch. For high-frequency carriers, these issues will be very dominant factors in determining the accuracy of time synchronization. So we try to come up with solutions that can cover different UE states. Thus, not just for the connected state, but also for UEs in either state inactive states. For this purpose, design of fast time synchronization for initial access or semi-initial access will be important, particularly for support of latency-sensitive applications. Another area is designing a proper frame structure suitable for the application. As an example, cycle time-based closed control would require careful design of frame structure so that it can accommodate coexistence of different cycle times that have different requirements in clock synchronicity. In this slide, we show analysis of error sources in time synchronization. So what we have found is that RX timing estimation error is the major factor causing the error. And this slide shows our preliminary result. Specifically, these are simulation results for a new synchronization signal. The simple modification of existing synchronization signals, as shown here, can dramatically enhance the synchronization performance. With this new sequence design, we find that the new synchronization signal is a lot more robust against frequency offsets and phase noise in comparison with 5G NR. Okay, the next topic is waveform for high Doppler. First of all, regarding mobility, we think 6G should support mobility of up to 1,000 km/h, but not sacrificing much the performance. And this is our proposal for the spectral efficiency targets in 6G. Since 4G LTE, WaveTM has been our main waveform. In general, multi-carrier modulation schemes like WaveTM are susceptible to Doppler spread. Doppler spread induces changes in subcarrier positions and breaks down the orthogonality between subcarriers, thus causing intercarrier interference. In case of WaveTM, if we increase subcarrier spacing to reduce ICI, intercarrier interference, it can result in a large CPU overhead in order to avoid ISI, inter-symbol interference. Thus, WaveTM has a trade-off between ICI and ISI. Another disadvantage of WaveTM is that high Doppler incurs rapid channel variation in time, thus causing a large DMRS overhead for channel estimation. So OTFS, orthogonal time frequency space, was introduced to remedy these issues. This is a 2D spreading scheme where data symbols are spread over time frequency resources. But the drawbacks of the OTFS are large processing delay due to spreading across multiple OTM symbols, and high computational complexity required for delayed Doppler domain equalization. More importantly, OTFS does not fundamentally solve the problems. Rather, the ICI in the time frequency domain is translated into channel selectivity in delayed Doppler domain. Based on these observations, we suggest a scheme called multi-block spreading-based multi-carrier. With this scheme, the time frequency resources are divided into n sub-blocks. Data symbols are divided into n groups, and each group mapped to one of the sub-blocks. Then we apply blockwise spreading. With this new waveform, we expect less processing delay when block spreading spans a small number of wavetime symbols, and lower complexity in equalization compared with OTFS if equalization is done on a by block basis, and also less interference between spread symbols. This is our simulation results comparing WaveDM, OTFS, and MBS-MC, our proposed scheme. So we tried TDLC channel model with different delay spreads and with UE speed of 500 km per hour. As expected, WaveDM is very sensitive to subcarrier spacing. That is, WaveDM needs to increase the subcarrier spacing to relieve ICI. In contrast, OTFS can get a better BLER with a smaller subcarrier spacing. This is because in case of OTFS, ICI is captured in delayed Doppler domain. Thus, ICI can be equalized, and performance is mostly affected by intersymbol interference. For the proposed blockwise spreading scheme, we tried a single SCS, subcarrier spacing 120 kilohertz with different block spreading sizes. What we have found is that proposed blockwise spreading scheme outperforms OFDM and the best case of OTFS. So also, we note that the proposed scheme achieves better performance with less delay and with lower complexity compared with OTFS. And these simulation results were obtained assuming ideal channel assumption. And now we are studying the effects of real channel estimation on the performance. Okay, this brings us to the end of my presentation. Thank you very much for your attention.
Thank you, Dr. Ko. It's a very interesting presentation. Especially, I'm very interested in the coming new waveform. We have used OFDM for 4G and 5G, but now IITRI is thinking of a new candidate as a new waveform for the 6G. It's a very interesting topic.